Okay, so in this video we will define the Markov chains or Markovian processes. Okay, we will give some examples. We will define the states and define the assumptions and properties of the Markovian process. Okay, so first of all, let's define the Markov chain or Markovian process. Okay, Markov chains. Okay, so Markov chains is actually a random process. Okay, it is a random process in which the future state of a process, object or phenomena actually depends on the current or the immediate preceding state. Okay, so Markov chain is a random process in which the future state, okay, or the next state of a process, an object or phenomena depends on the current or the immediate preceding states. Okay, now we will define the states. Okay, so state is actually a condition or what we call location of certain object or process. Okay, condition for a process and location for the object, okay, in a system at a particular time. Okay, particular time, because Markov chains are very related to the time period. Okay, it is a time period based phenomena or process. Okay, so for example, the states can be defined as, for example, we have a machine, okay, working in a manufacturing setup. Okay, so this machine actually, it can attain two states. Okay, it is either idle or stopped, okay, or it is in working condition. Okay, working. Okay, so these two are the states. So let's, for example, the idle state is represented by I and the J represents it is working. Then the probability that the machine goes from the initial stage of idleness to the working condition, okay, it is called the transition probability. Okay, probability, and it is mathematically, it can be written as the probability that the object is at next stage J at time period is equal to 1, such that the current stage or the initial state Si is at time period of t is equal to 0. It means that the probability that the initial state of certain object or a system or a process is Si. Okay, initially at time t is equal to 0, it is in the state Si. Okay, let's do it in this example. For the machine, the Si is the idle, so the probability that the machine goes from idleness to the working condition, okay, it can be mathematically written as the probability that the next state J is working for the machine such that initially the machine is idle. Okay, so this is the transition probability Pij, where I is the initial state, okay, and j is the next state. Okay, in this condition I is the idle and j is the working state for the machine. Okay, so these two are the states for this machine. Similarly, another example, let me give it another example. Okay, another example is, for example, we can say about weather. Okay, weather system. Okay, so it can either be like cloudy, raining, and clear. Okay, cloudy, raining, and clear. These three are the states. Okay, so the probability that initial is clear or cloudy and it goes to rain, for example, the PCR, that it is a probability, the transition probability that we have a cloudy weather and it starts to rain, it goes into the state of raining. Okay, this is for example equal to 0.5. Okay, 50% chances we have. Okay, so we can actually model this system like this. Okay, so this arrow shows that the initial stage was cloudy and it started to rain and it has a probability of 0.5. Okay, and the probability of rain to clear or see clear, okay, this is equal to 0.3, for example. Okay, so this is 0.3. Okay, and similarly the probability that it was cloudy and it remains cloudy, PCC, it will be equal to, this is 0.5, this is 0.3, so the total probability 0.8 is the total probability that we have right now. 0.5 for from cloudy to raining and 0.3 from raining to clear, and we know that the total probability is equal to 1. Okay, so the probability from cloudy to cloudy will be 0.2 or equal to 1 minus 0.8. Okay, which is 0.2. Okay, I will explain this later on, because the row probability, it is equal to 1 actually. Okay, like for example, if we have like 3 states, so it will make a 3 cross 3 matrix. Okay, the transition probability matrix TPM is equal to, this will be 3 cross 3. Okay, because we have 3 states, state 1, state 2, and state 3. Okay, this is the initial state C, R, and clear, CL. Okay, so from cloudy to cloudy, this is the next, these are the initials, these are the next. Okay, R and CL. Okay, so when it is cloudy and it remains cloudy, we have a probability of 0.2. so P11 is equal to 0.2. okay, that it has initial state of 1 and the next state is also 1. Okay, and from cloudy to raining it is 0.5, and from cloudy to clear it is 0. This will be 0.3, because we have 0.2, 0.5, 0.7, and the total sum of the rows, actually this row, it should be 1. So 1 minus 0.2 minus 0.5, it equal to 0.3. Okay, so in exam you may be given, like you may be given the cloudy to cloudy and cloudy to raining, but you may not be given from cloudy to clear. Okay, so you can find it by the summing or summation, find the summation of these rows, okay, and equating it to 1. So you will get 0.3. Okay, and similarly you can put all these probabilities. So this is the transition probability matrix. Okay, I will define the transition probability matrix in the next video. Okay, I will give you another example, and then I will explain the transition probability and transition probability matrix, how to make it, and then we will move on to the how to find the probability of certain state. Okay, so talking about the transition probability, okay, transition probability TP, okay, it is the probability of going from initial state to next state, okay, from I to J, or recurring the same state again. Okay, so when we talk about the transition, actually, okay, so if a system in state I, it can also get into the same state I for the next time period. Okay, for example, we say that a machine has initial state of running, okay, at t is equal to 0. Okay, so it can also be running in the next hour t is equal to 1. Okay, so it will retain the same state. Okay, we do it graphically by, like, for example, here we have like a running state. Okay, we say that the initial state is running state. Okay, and we have another idle state as the next state. Okay, so graphically we do this by this arrow. We started from the running state and again pointed to the running state, and we say that it has a probability of 0.9. It means that a running machine in the previous state will be running in the next state with the probability there is 90% chance. Okay, so the probability is 0.9. Okay, and running to the idle it will be 0.1, because the total probability is 1.0. So 1 minus 0.9 will become 0.1. Okay, and if a machine is in idle state, initial state is idle state, and it remains idle in the next, it is 0.2, for example. Okay, and if the machine is idle and the next state is running, okay, so it will be 1 minus 0.2, which will be equal to 0.8. Okay, so we have two states over here. So the transition probability matrix, okay, actually it will be a 2 cross 2 matrix. Okay, and it will be the running state and idle state, and the future are also running and idle. So the probability that the initial state is running and the next state is also running is 0.9, and the probability that the initial state is running and the next state is idle is 0.1. Now if we sum both these, it becomes 1.0, that it should be. Okay, you should always get the sum of the rows equal to 1.0. Okay, and the probability that initial state is idle and the next state is running, okay, idle to running is 0.8. Okay, and probability that initial state is idle and the next state is also idle is, it will be 0.2. How? Because the total sum of the rows, it should be equal to 1.0, and 1 minus 0.8 is 0.2. So this is the transition probability matrix for this two state conditions for a machine. Okay, and the transition probability is the probability of going from one state to another state in a certain time period, okay, or recurring the same state again in the next time period. Okay, this is the transition probability, and I have given you a detailed example with the two states of the machine. Okay, so in this scenario, actually the system is the manufacturing plant, okay, and the states are running and idle state of the machine, and the transition probability is these probabilities of converting from running state to idle and from running to again running condition in the next hour. The time period is hour, 1 hour. For example, we get it like that at t is equal to 0, it means that initial hour of the running, okay, and t is equal to 1 mean in the next hour. Okay, so the time period here is hourly, and this is the transition probability matrix. Okay, so we have some assumptions, okay, that we consider in the Markovian process or Markov chain. Okay, these assumptions are: the number one is that the number of states okay, of a system are actually finite. We don't have any infinite number of states. The second assumption is that the states are mutually exclusive. Okay, it means that we can have one state at a time. We cannot have two states at the same time. Okay, like the machine can either be running or idle at certain time. Okay, it cannot be both. Okay, the third is that the states of the system are collectively exhaustive. Okay, this means that all states that the system can have or the process can have, all states are known to us. Okay, we know that the machine can either be in a running state or in idle state. Okay, so the states are collectively exhaustive. Okay, we know about all the states of the system. Okay, the fourth one is that the probability of moving from one state to another state is constant over time. Okay, the probability of moving from one state to another state actually is constant over time. It means that the probability that we have, like here from running to running, is 0.9. It will not change over time. Okay, it will remain 0.9. Okay, this will not depreciate and it will not increase, it will remain the same. Okay, so these are the four main assumptions of the Markovian process or Markov chain. The first one is that the number of states are finite. We have a finite set of states, like running and idle. We have two states, which is finite. Okay, the states are mutually exclusive, only one state at a time. Okay, and state are collectively exhaustive. It means that we know about all the states that a system can attain. Okay, and the fourth one is that the probability of moving from one state to another is constant over time, it will not change. Okay, so these are the four assumptions of the Markovian process. Okay, now we will discuss some detail about the transition probability matrix. Okay, how it is used. Okay, and then we will talk about the single step transition probability, two step, and n step transition probability. Okay, and then we will know about the assumptions of the transition probability matrix. Okay, I will continue that into the next video. Okay, and okay, so we will now discuss the transition probability matrix in detail. Transition probability matrix. Okay, so we know that we have probabilities of going from one state to another state of each system. Okay, and it is deterministic if we know the initial probabilities of the system that the system has. For example, if a system has like 3 states, okay, or 2 states, like the machine probabilities is equal to 0.5 and 0.5. Okay, there are 50% chances that the machine is at running condition and 50% chances that the initial condition is idle. Okay, now these initial probabilities are known to us. Okay, so this system is deterministic. Okay, deterministic Markovian process. Okay, because we know about the initial probabilities of the system. Okay, so the transition probability matrix, okay, this thing, okay, it is used to predict the movement of system from one state to another state. Okay, so it, using the behavior of the system, it predicts the movement of the system from one state to another state. Okay, so it is defined by the transition probability matrix TPM, known as TPM transition probability matrix. The order of this matrix, actually, it is the number of states multiplied by the number of states. Okay, so if we have 2 states, then TPM is a square matrix of order 2 cross 2. Okay, if we have 3 states, then the TPM is a square matrix of order 3 cross 3. Okay, TPM is always a square matrix because it has the probability of, you know, the initial states and going into the final states. Okay, so the number of initial states is also equal to the number of the final states, so that is why it is a square matrix. Okay, and it is denoted by P is equal to, okay, these are the initial states. Okay, initial states at n is equal to 0. Okay, this is stat 1, 2 and 3. These are the initial states, and this is stat 1, 2 and 3. These are the final states at n is equal to 1. Why I wrote n is equal to 0 and n is equal to 1? Because we have the degree of P is equal to 1. It means that it covers only one time duration. Okay, from n is equal to 0 to n is equal to 1. Okay, so this probability is P11, which is the probability of going from state 1 to state 1 again, regaining the state 1. Okay, and this is P12 from one state to second state, and P13 from state 1 to state 3. Similarly here, P21 from initial state of 2 to 1, P22, regaining the state 2 from state 2, okay, and 2-3 going from state 2 to state 3, and this is the P31 going from third state to the first state, 3-2 going from the third state to the second state, and P33 regaining the third state from the third state, okay. The diagonals are always the recurring or regaining, the diagonals are regaining, okay. Diagonals probabilities are the regaining same state, okay, same state, okay. These are the upper what we say, the triangle, this triangle, this is the gaining, okay, and this is the losing. The lower triangle is losing because it is going from 2 to 1, so it lose. From 3 to 1, so it lose. From 3 to 2, it is losing the state. This is the gaining the state, okay. From 1 to 2, 1 to 3, and 2 to 3, okay. And 1, 1, 2, 2, and 3, the diagonals are regaining, okay. So this is the transition probability matrix, okay. And P11 represents from state 1 to state 1 regaining, okay. This is state 1, okay. So this is the regaining of the state 1 again, okay. P12 is from state 1 to state 2 and so on, okay. We can define each probability, okay. So this, when we have the degree of the P as 1, this is called the single step. Second step transition probability, okay. In this we define only the 2 time periods, okay, for n is equal to 0 and n is equal to 1, okay. So this is the single step because we make a step from 0 to 1 or from 1 to 0, okay. So this is single step. Similarly, we can have like 2-step transition probability, okay. 2-step transition probability, okay. And this, the P will have like a square degree, okay. We have same 1, 2 and 3 states as initial, and 1, 2 and 3 states as the final, okay. And here we have P11 square, P12 square. We just take the square of each of the probability, okay, and so on. P33 square, or P square is equal to 1, 2, 3, 1, 2, 3, okay, okay, and taking the square of this whole matrix, which is equal to, which is same to same thing, okay. And what this P11 square represents is the probability, okay, that the system has state 1 at n is equal to 2, such that the system has state 1 at n is equal to 0, okay. So the initial state at n is equal to 0 is state 1, at it regains the same state at n is equal to 2. The time period is now 2 because we have square over here, okay. And similarly defining all that, for example, I define P12, okay. So this is the probability that the final state, okay, the final state is state 2 at n is equal to 2, such that the initial state is state 1 at n is equal to 0. This is the P12 square, okay. So this is how the 2-step transition probability is defined, okay. And we will use these probabilities to predict the exact movement of the system from one state to another state. Okay, given that we have the given initial transition probabilities, okay, initial system probabilities, sorry. Okay, there is a theorem against it, and I will also explain the theorem and make some example based on that theorem. Okay, so now moving on to the n step transition probability. Okay, we have now n step transition probability. Okay, we can actually generalize the p1, p square, p3 or p cube or p raised to the power 4 into a generalized n system, okay, which is p raised to power n. Okay, and it is equal to 1 2 3 p11 raised to power n, p12 raised to power n, and so on. Okay, and it is equal to this probability raised to power n. Okay, if we take the n power of that matrix, we take exactly the n step transition probability. We define the n step transition probabilities. Okay, so this is the generalized form of the transition probabilities. So n can be 1, n can be 2, n can be 3, n can be 4, and so on up to p raised to power n. Okay, so no matter what the n attains a value, we can just use it and we can define the n step transition probability. Okay, so now we will define some of the assumptions of the transition probability matrix. Okay, assumptions of transition probability matrix TPM. Okay, the first assumption is that the sum of each rows is equal to 1. It means that this p11, p12, p13, p11 plus p12 plus p13, it should be equal to 1. Okay, so in the exam or in any question, if you are given p11 or p12, we can define the p13, or if you are given p12 and p13, we can define the p11 by using this equation. Okay, so this is very important. Teacher may trick you in this particular assumption. Okay, he may give you like 2 probabilities, but he may not give you the third probability. So the third probability can be defined by using this summation and equating it to 1. Okay, the second is that the probability Pij, okay, it must be greater than or equal to 0 and less than or equal to 1. So it is between 0 and 1 and it is non-negative. Okay, a probability cannot be negative. Okay, and the third one is that the TPM is always a square matrix of order the current into the next states. Okay, number of states will define the order of the transition probability matrix, or the number of states multiplied by number of states, number of initial states into number of future states. Okay, this will define the order of the TPM. So these three are the assumptions of the TPM that we must know about. Okay, now I will go to some practical examples of the transition probability matrix and some theorems. Okay, so in this video we will solve a few examples. Okay, and we will know how to build a transition probability matrix interpret the state transition matrix in terms of retention, and we'll draw the transition diagram. Okay, so the question is that in a certain market only two brands of cold drinks A and B are sold. Okay, given that a man last purchased brand A, okay, given that a man last purchased brand A of cold drink, okay, there is 80% chance that he would buy the same brand, that he would buy same brand A. Okay, and next purchase. While if a man purchase brand B, if a man purchased brand B, there is 90% chance that his next purchase would be brand B again. Okay, they are saying that using this information, first develop transition matrix, and secondly develop transition diagram. Okay, so let's start with the transition matrix. Okay, now we have two brands. Okay, so these are the states of the system. Okay, so we have brand A and brand B. Okay, so it will be the TPM transition probability matrix will be a 2x2 matrix. Okay, this will be a 2x2 matrix. Okay, AB and AB. This says that given that a man last purchased brand A, it says that if the initial state is brand A, there is 80% chance that he would buy the same brand. Okay, so probability of retaining A from A is 0.8. Okay, and if a man purchased brand B first, there is 90% chance that he would buy brand B again. So from B to B, the chance is 0.9. Now we know that sum of the rows it is equal to 1. It means that the probability of AA plus probability of AB is equal to 1. So probability of AA is given to us 0.8 plus probability of AB is equal to 1. So probability of AB is equal to 1 minus 0.8, which is equal to 0.2. So this is equal to 0.2. Okay, similarly this is 0.9, so 1 minus 0.9 is equal to 0.1. Okay, so going from B to A, okay, if you purchased B product first, and the probability that he will buy next product A will be 0.1. Okay, so the sum of the rows 0.8 plus 0.2 is equal to 1, and 0.1 plus 0.9 is equal to 1 also. Okay, so the transition probability matrix is constructed. Okay, now in the second part of the question, they say that develop the transition diagram. Okay, so how to make a transition diagram? We first define the two states. Okay, two states are defined. Now they say that the from A to A again, okay, the transition, the probability is 0.8, and from A to B, okay, this transition is equal to 0.2. The transition probability is 0.2, and from B to B we have a transition probability of 0.9, and from B to A we have a transition probability of 0.1. Okay, so this is the transition probability diagram being developed. Okay, we have a theorem over here. Okay, and it states that, like, if we want to find that in the nth transaction the system will land at state J, okay, then probability that xn is equal to J, okay, this is equal to summation of okay, this is a summation of the probabilities that xn is equal to J such that the initial state is I multiplied by the probability that the initial state is at I, okay, or the probability I j raised to power n is equal to ai into p raised to power n. This is the simpler form of this theorem. In this theorem, this ai, this is the initial state probability. Okay, this is the probability that the initial state is at the I. Okay, initial state is equal to the ith state. Okay, and this is the nth power of the TPM. Okay, transition probability matrix. Okay, so when we multiply the probability that initial state is at I state and with the nth power of the TPM, we find that the nth transaction, or we can say the transition of the system will land at state J. Okay, it means that after n transitions, the state of the system will be jth or J state. Okay, such that the probability of the initial state is I is given to us, and we have the TPM from the system. Okay, I will solve some question on this, then you will understand it. Okay, and this Pijn, this is equal to actually the probability that system will go from or transit from state I to state J in n number of transitions. Okay, or n number of steps, or n steps. Okay, we already discussed the n step TPM. Okay, so it will be equal to the TPM raised to power n multiplied by ai. Okay, where ai is the probability that the initial state of the system is I. Okay, now to prove this theorem, actually the theorem says that the probability of the nth transaction is equal to the probability of the n power of the probability matrix. Okay, so to prove this, actually what we do is we say that Pij raised to power n is equal to probability that xn, the nth transaction, lands at j, where the initial transaction is at I. Okay, we know that this is the universal truth. Okay, this is something that we know. Now if we put n is equal to 0, so Pij raised to power 0, it is equal to the probability that x0 is equal to j such that x0 is equal to I. Okay, so this will give us a value of 1 if I is equal to j. Okay, it means that if the system retains its initial condition, okay, and it will be 0 if I is not equal to j. It means that we have like two states. Okay, for example, s and t. Okay, and we have two future states, s and t. Okay, so if I is equal to j, so if s is equal to s, then the probability is 1, and if not, it is equal to 0, and from t to s is 0, and from t to t, because I is equal to j, okay, this is equal to 1. Okay, this thing is equivalent to this matrix. Okay, now it gives us as an identity matrix. Okay, this is 1 1 and these diagonals are 0 zeros, so it is an identity matrix. So we say that p raised to power 0 is equal to p naught, it is equal to identity matrix. Now if we put n is equal to 1, so Pij 1, okay, it is equal to the probability that x1 lands in j such that x0 is in the I. Okay, so it is the same TPM matrix of first order. Okay, similarly, if n is equal to k, okay, in generalized form, so p raised to power k is equal to pk. Okay, this is the generalized form. Now if you put n is equal to k plus 1, okay, for n is equal to k plus 1, we see that if it still holds, okay, so we say that Pij raised to power k plus 1, okay, it is equal to the probability that the k plus 1 stage lands in j, okay, such that xk, okay, the kth is s and the initial stage is at ith, okay, multiply by the probability that the kth is equal to s such that initial is equal to I. Okay, so this thing actually, this according to this, let me know, this is same thing, this one is same thing if we see this thing. Okay, these are the two states consecutive to each other. Okay, so this will give us a probability PIS, okay, raised to the power k, because it is for the kth transaction. Okay, so Pij raised to power k plus 1 is equal to the k plus 1 is equal to j if the kth transaction lands in s and the initial one is at I. Okay, multiplied by this will give us the probability of I s raised to the power k, because this is the k transaction. Okay, so now let's connect the s and the j state only. Okay, remove this one. Okay, because we have the initial from s equal to this. Okay, from I to s we have this transition probability. Okay, and from s to j we will have, now this is going in two steps. Okay, first from I to s and then from s to j. Okay, so it will be equal to summation of s is equal to 1 up to n. S is now the initial stage. Okay, pis, okay, raised to power k multiply by probability that x1 is equal to j such that x naught is equal to s. The initial now is s and the first is j. Okay, multiply by the probability that the initial is I and the next is s state. Okay, raised to power k, it is the kth transaction. Okay, so this is the this equation. Actually it will be, if it is simplified, okay, the pis raised to power k into psj. Okay, this states that this thing, okay, this states that from I we go to s state and from s we go to the j state. Okay, so we have the probability from I to s and we have the probability from s to j in k transactions. Okay, so if it is simplified, actually it gives us probability of raised to power k into p ij. Okay, so it is exactly same as p raised to power n is equal to p n. Okay, and this thing is equal to p raised to power k plus 1. Okay, so this is the theorem. Okay, when we solve questions on these, you will come to know and you will understand this. Okay, I will solve an example and then you will see for yourself. Like, okay, we have an example actually which says that, it is the book example actually done by the professor. It says that consider the probability transition of a DTMC. Okay, the probability transition of DTMC. Okay, DTMC we already defined, it is the deterministic Markov chain. Okay, in the deterministic Markov chain we know the exact probability of the initial stage. Okay, so the TPM we have like 3 states. Okay, and the TPM is okay 0 0.2, 0 0.3 and 0 0.5. so the sum of the rows is equal to 1, 0 0.10, 0 0.9. this is also 1.55, 0 and 0 0.45. this is also is equal to 1. Okay, and the initial state probabilities, this is 1, 2 and 3. we have 3 states. Okay, these are the initial stages, these are the future states. Okay, so the initial state probabilities A is equal to 0.1, 0.4 and 0.5. It means that the probability that the system is initially at state 1, okay, it is 0.1, only 10% chances, okay, and the probability that the system is initially at state 2 is 40% chances or 0.4, okay, and the probability that the system is at state 3 initially is 50%, okay. So these are the initial states probabilities, okay. It says that find the probability mass function of okay, PMF of x3. It means that the third transaction, okay, or the third transition, okay. So we know that a raised to power n is equal to a into probability matrix raised to power n, okay. So a3 is equal to a into p raised to power 3, okay. So okay, so this is equal to 0.1, 0.4 and 0.5 multiplied by the 0.2, 0.3, 0.5, 0.1, 0, 0.9, 0.55, 0, 0.45 whole cube, okay. So we can find the cube of it and multiply it with this, and we will find the probability of the x3, the PMF of x3, okay. Okay, so 0.1, 0.4, 0.5 multiplied by, when it is raised to third power or made cube of it, it goes 0.40, okay. If we want to calculate the cube, we can also calculate cube of the individuals, okay. It will give us the same values, okay. 0.104 and 0.494, okay. Here we get 0.356, 0.15, 0.49 and 0.35, 0.107, 0.54, okay. When multiplied with this one, let's see. So this comes 0.3574, 0.1239 and 0.5154. It is equal to a cube. And what does it means? It means that if the initial state of the system is 1, so the third state, the probability that the third state is also 1 is 0.3574, okay. This states that the second one, that if the initial state is 2, so the third, after the 3 steps, the state of the system is 2 is 12.39% probability, okay, and 51.54% probability that if the initial state of the system was state 3, okay, and after 3 transition the system lands in again in the state 3, okay. This is the PMF of the system after 3 transitions. Okay, so in this video we will discuss the occupancy time, okay. Occupancy time. This is the actually the time Markov chain spins at specific state, for example J, okay, during a time period. Okay, so we know that there are n number of transitions, okay, starting from state I to J. It can happen in n number of transitions. This n transition, it can be 1, this n can be 1, 2, 3 and up to k. Okay, so the time a Markov chain spends at state J, for example, okay, during the time period, okay, in n number of transitions, okay, this is called the occupancy time. Okay, this occupancy time, it's defined by a occupancy matrix M of k. Okay, so matrix of occupancy are occupancy matrix. Okay, this is defined by mk, okay, and it is equal to mij k, okay, where mij is equal to the time spent in state J such that initial state was state I. Okay, the initial state is state I and the final state is J. So the time spent in this state J while the initial state was I is called the occupancy time. Okay, so we have a theorem over here, okay, and this theorem states that this mk, the occupancy matrix, it is equal to summation of r is equal to 0 up to k into the probability transition matrix raised to the power of r. It means that, for example, we wanted to find it for the 3 transitions or 3 steps, okay, for example 3 steps. For example, it means that r is equal to 0 up to k, and this k is equal to 3. Okay, from r0 to 1, 1 to 2 and 2 to 3. Okay, so it will be equal to summation of, okay, r is equal to 0 up to 3 and p raised to power r. So r is equal to 0, 1, 2, okay, sorry, 2, 0 and 1, 0, 1 and 2, okay, k is equal to 2, okay, because we have 3 over here. So we will have like p0 plus p1 plus p2. Okay, when we sum these, it will give us the exact time a Markov chain MC spends in state J while the first state was I. The initial state was state I. Okay, now we will do an example on it, okay, and then after that we will do it on the scientific workplace also. Okay, because if we have like 5 or 6 steps, then it is quite time consuming to calculate each one, and then add it. Okay, so scientific workplace can do it like quite easily in a matter of seconds. Okay, so this is another problem that we need to solve using the Markov chain process. Okay, we have a transition probability matrix for 3 states which is given. Okay, S for sunny, C for cloudy and R for rainy. So we have 3 states. The initial states are sunny, cloudy and rainy, and the final states are also sunny, cloudy, and rainy. Okay, it states that if at first day, okay, if it's sunny, so there are 50% chances that the next day is also sunny, and 30% chances that the next day is cloudy, and 20% chances that the next day is rainy. Okay, and if it is cloudy at the first day, okay, there are 50% chances that it is sunny on the next day, 20% chances that next day it is also cloudy, and 30% chances that it is raining on the next day. If it is raining on the first day, there are 40% chances that the next day it is sunny, and 50% chances that it is cloudy the next day, and 10% chances that it is also running the next day. Okay, so the question says that starting from today is sunny. Okay, if it rains on 7th and 8th day, okay, the insurance will pay $2,500. Okay, and they are investing $200 to buy this insurance. Okay, so should they take the insurance or not? We have to decide based on this transition probability matrix. So what we need to do is we need to find the expected value. Okay, the expected value that for this $2,500. Okay, so expected value, if it rains, okay, it is equal to 2,500, which is the price money, okay, multiply by the probability that it rains on the 8th day, such that it rains on the 7th day and it is sunny on the first day. Okay, now from this is done in two steps. Okay, first, from first day, that is sunny, we have to move to the 7th day, and then from 7th day we have to move to the 8th day. Okay, it is done in two steps. Okay, so it is equal to 2,500 multiplied by, okay, multiplied by the probability, okay, probability that x8 is equal to 3 means it is raining. Okay, s is equal to, here, okay, s is equal to 1, sunny is equal to 1, cloud is equal to 2, and raining is equal to 3. That is why I am writing x8 is equal to 3 over here. I can also write x8 is equal to r, okay, such that x7 is equal to r and x1 is equal to s. I can also write it as, okay. So probability that x8 is equal to r, such that x7 is also raining, okay, multiplied by the probability that x7 is equal to raining, such that x1 is equal to sunny. Okay, this is divided into two steps, from 1 to 7 and from 7 to 8. Okay, now from 1 to 7 it is done in 6 steps. Okay, it is done in 6 steps, so it is equal to 2,500 multiplied by, and this is done in one step. 7 to 8 is one step. Okay, so it is equal to p r r, okay, because on 7th it is also running and in 8th it is also running. Okay, p r r raised to power 1, because it is done in one state. Okay, one transition. Okay, multiply by probability of s to r. Okay, initial is s, final is raining, sorry, and it is done in 6 steps. Okay, so when we do this, we find out the value of the expected revenue. Okay, expected cost. Okay, okay, So this is done in 6 steps. Okay, so what we need to do is we need to find the 6th power of this initial TPM, which comes out to be this thing. Okay, this is the state: sunny, cloudy and rainy, sunny, cloudy and rainy. Okay, so if at first day it is sunny, on the 7th day it is raining, the probability is 0.21. Okay, so this is equal to 0.21, and this is only done in first step, one step. Okay, so this is the first one to the power 1. Okay, so if it is raining on first day and it is raining on the next day, its probability is 0.1. Okay, its probability is 0.1 multiplied by 2500. Okay, so when we multiply it, we get 52.5. Okay, this is the expected revenue or expected value when it is raining. Okay, now the initial investment that they are doing is equal to $200. They are paying $200 for this insurance, but the expected amount, okay, that they are receiving actually is $52.5. So 52.5 is less than $200 actually, so they should not consider this offer. They should not go for this insurance. Okay, I hope you have found this example useful. Okay, because we used the actual theorem in here in 2 steps. Okay, so this thing is important to understand. Okay, so in this new example, okay, this question actually we have 3 states transition matrix. Okay, we have 3 states, so 1, 2, 3. Okay, these are the current states, 1, 2 and 3. These are the future states. Okay, from 1 to 1 the probability is 0.2 and 0.3, 0.5, transition from 1 to 3 and so on, 0.10, 0.00 and 0.90. okay, and we have 0.55, 0.00 and 0.45. okay, these are the probabilities of transitioning from one state to another. Okay, so the retention of 1 to 1, it is 20% chances. From 1 to 2 it is 30% chances and 50% chances from 1 to 3. And if initial state is 2, from 2 to 1 going back to 1, it is 10% chances. Regaining the same state again is 0% chances, and from 2 to 3 it is 90% chances, and so on. Okay, so we have this transition probability matrix P. Okay, this is the transition probability matrix P. Okay, now they say that this is example 2.13 in the book, Kulkarni book. Okay, and it says that find M10. Okay, find Mij of 10. Okay, it means that for k is equal to 10 we need to find the occupancy matrix. It means that we need to find or compute the occupancy matrix. Okay, after 10 steps or 10 transitions. Okay, after 10 time periods, they say that what is the average positioning time or average state time in state 1, state 2 and state 3, if the initial state is 1, 2 or 3 respectively. Okay, so how we find it? We know that m of k is equal to summation of r is equal to 0 up to k or n, anything you want to write. You can write m of n over here, but we have written m of k over here, so I will change this n to k. So from r to 0 up to k, and p raised to the power of r. Okay, so using SWP, because we want to find m of 10, so summation of p raised to power 1 up to 10, it will be kind of very lengthy process. So we will use the SWP to find this m of 10. Okay, so let's do it in the scientific workplace. Okay, so let's have like another blank sheet. Okay, now this is the blank sheet. What I need to do is I need to go to control M for mathematics. I need to define the function first, okay, which is m of k is equal to shift m of k is equal to, okay, this is 3 cross 3 matrix, okay, because we have 3 states, so it will be 3 cross 3 matrix. Okay, so defining a 3 cross 6 over here. Okay, in the first one we have a value of 0.2, okay, 0.2, 0.3 and 0.5. okay, 0.1, 0 and 0.9. In the third row we have 0.55, okay, 0.00 or 0 and 0.45. okay, now sorry, this is p, so you can define it as control M shift p is equal to, and need to define this, okay, control n equal to. Now we have the matrix, but we didn't have the function. Actually I needed to define the function first. Okay, so it is equal to summation of, this is control L, so it will define the lower limit. Lower limit is r is equal to 0, space bar, so it will go to the normal writing. I need to control to find the upper limit. To define the upper limit, I need to do the control H, so it will go to the upper limit, and in upper limit I need to write k. Okay, space bar, so it will return to the normal writing, and I need to define the p matrix over here. Okay, and raised to the power r. Okay, and I need to define this. To define this, I need to go to control n equal to, okay, and return to the third row. Okay, now we have defined both of these actually, so let's see if they are defined. Okay, show definitions, and we have the matrix and as well as the function both defined. Okay, so now we are good to go and make the calculation. Now I need to find is, in this example I need to find the occupancy matrix after the 10 iterations or 10 after 10 time period span. Okay, so I need to calculate m of 10. So for that I need to copy this. Okay, control C, control V, and in this k I need to replace it with 10. Okay, I need to now select it and press control E. So it has now given me the occupancy matrix after 10 iterations or 10 time period span. Okay, so after 10 time periods, actually 10 time periods, if the initial state is 1, okay, so this much time it will regain the same spot, it will go to the second state this much time, and it will go to the third state this much time. Okay, and this summation of row. Okay, so in this video what we will be doing is we will be solving this occupancy time problem in the scientific workplace. Okay, so here are some steps to follow for doing it in the SWP. Okay, first of all you need to define m of k, okay, which is equal to summation of r is equal to 0 up to k probability transition matrix raised to the power of r. When you define this, after this what you have to do is you have to define the value of this R or K. Okay, so you need to find, like for example, we want to find the m of 5. Okay, so what the computer will do is it will define it from R is equal to 0 up to 5 and probability of R. Okay, so it will first put the value of R is equal to 0, R is equal to 1, R is equal to 2, 3 and so on, and it will find the exact value of it. Okay, so now we will do the same thing in the scientific workplace, and for that we need to select a problem to solve. Okay, so let's select a problem from the exercise or from the examples and then solve it using scientific workplace. Okay, so we have the weather example. It says that the probability transition matrix, it is equal to, we have three states, so it will be a 3 cross 3 matrix. It is 0.5, 0.3, 0.2. Okay, 0.5, 0.2 and 0.3, 0.4, 0.5 and 0.1. Okay, we have state 1, 2, 3, future state 1, future state 2, future state 3. Okay, so it is 3 cross 3 matrix because we have 3 states. Okay, the first state is sunny, the second state is cloudy, and the third state is rainy. Okay, what we need to do is they want us to compute, okay, compute the mean number of rainy days. Okay, mean number of raining or rainy days in a week. Okay, in a week. Okay, assume that, okay, assume that the first day is rainy day. Okay, sunny day. First day or today, starting from today, is sunny day. Okay, so the P of 1 is actually the, sorry, A1 is sunny day. Okay, now the first day is sunny day, x1 is sunny. Okay, so what we need to do is we need to find this Mij. Okay, so I is sunny 1. Okay, and j is rainy. Okay, in 6 transitions. This is need to be find. So k here is equal to 6. Okay, so what we need to find is we need to find m of 6. Okay, is equal to summation of r is equal to 0 up to 6 probability of r raised to power r. Okay, and it will place value of r is equal to 0 up to 6. So it will get us the exact this thing. Okay, and then from the probability matrix that we define it, okay, which is called the occupancy matrix, in that occupancy matrix we need to go for 1 and 3, 1 in the starting and 3 in the future state. Okay, I will do it in the scientific workplace and you will get to know it how to do it. Okay, so we have now a blank sheet of the scientific workplace. What we need to do is we need to define the occupancy matrix first. Okay, occupancy matrix is equal to m of m of k. Okay, it is equal to summation sign is this one. Okay, let it in. Okay, this is the sum sign. Okay, so pick this sign. Okay, summation. Now I go to control L. So it will define the lower bound of it. For in here we need to write r is equal to 0. Okay, now space bar, and it will go to the normal writing. I need to now write the upper limit. So for the upper limit I need to do is control H. So it will go to the upper bound. In upper bound I need to write only K. Okay, and space bar. It will get to the original, what we say, normal writing. Okay, now I need to define the transition probability. Okay, this is by capital P, and I need to power it to the raised to the power of r. Okay, so control H and writing r and space bar. Now I need to define it. Okay, so selecting it and control is equal to, oops,